Hi everyone, it's wonderful to be here with you today. The AI transformation happening in technology today is monumental, and today we are going to be talking about our work at Google, both to enable it and to simplify its adoption. Generative AI is not just another technological advancement. I see this as truly the biggest transformation since the rise of the internet. If we think back 30 years ago, when we saw the development of the World Wide Web, most people, even those in and around technology, wouldn't have predicted exactly how much the world would change. I think we are in that moment right now. None of us are able to truly predict what's going to happen in the next 4 to 5 years. But I think it's safe to say the change and impact we will experience with generative AI will go beyond what any of us can imagine right now. We're on the cusp of a change that will redefine industries, amplify human potential, and create unprecedented opportunities. Today, we're here to talk about how this innovation is applied in your organizations, enterprises. We do this by optimizing for specific workloads, from migrations to cloud-first workloads. And of course, we're investing heavily in optimization for AI workloads, where today I have several incredible new launches to share. What makes Google so unique for AI workloads is our unified technology stack. Because we manage the entire stack, from chips to models, we're able to leverage each aspect of the stack to achieve a greater goal. For example, we've got cutting-edge AI models, including our latest releases, Gemini 1.5 Pro, which has an incredible 2 million context window, and Flash, which is nearly 2.5 times faster than GPT-4o Mini. And at the AI platform layer, we have Vertex AI, which makes it easy to access, evaluate, customize, and deploy these models at scale. The combination of models and platform has been pretty revolutionary. In fact, we've witnessed a staggering 36x increase in Gemini API usage on Vertex AI this year alone. Because of our unified stack, Vertex AI customers get the benefit of our infrastructure by default. It's easy to configure compute resources, including TPUs and frameworks like PyTorch, right from within Vertex AI. So let's take a closer look at that infrastructure. At Google, we deliver this through AI Hypercomputer. Based on years of Google's own experience of delivering AI at scale, AI Hypercomputer is a composable architecture designed specifically for AI workloads. It spans everything from hardware to software to consumption and can be flexibly deployed, which is essential for adapting to the enormous variety and rapid growth in models and use cases. For example, last month at our Gemini at Work event, we shared how Snap uses our Gemini Flash model to power Snapchat's My AI chatbot, answering everyday questions and solving problems for their hundreds of millions of users worldwide. But what's actually behind these Gemini Flash models serving the answer? AI Hypercomputer. Snap is also serving their 800 million monthly active users with NVIDIA GPUs in Google Cloud via a priority expander service built with GKE to power their many recommendation models. The AI Hypercomputer architecture unifies multiple layers of technology and infrastructure into a scalable solution. What almost all of our customers are looking for is infrastructure with better performance, dramatically simpler development models, and to do all of this with lower cost. This is why we're enhancing AI Computer across all of these areas. Starting from our own custom AI silicon, Tensor Processing Units, or TPUs. The story of TPUs starts over a decade ago, when a group of Googlers showed that we'd need to more than double the number of computers in Google data centers to handle the emerging AI use cases we were anticipating. We knew we needed a better way, and so in 2015, we deployed the first TPU for internal workloads. Since then, TPUs have been used to power search, photos, maps, and many of our globally available services. TPUs were also used to train AlphaFold 2, a groundbreaking scientific AI system developed by 2 Googlers who recently received a Nobel Prize for their work in the discovery. What makes a TPU unique is that it's a chip designed with a single, specific purpose, running the unique matrix and vector-based mathematics needed for building and running AI models. And we couldn't keep this innovation to ourselves. So starting from the second generation of TPUs, V2, we began offering them to you, our cloud customers. Today, I'm pleased to announce that Trillium, our 6th generation of TPUs, is now available in preview. Trillium delivers an impressive 4.7x increase in compute performance per chip with twice the high bandwidth memory and bandwidth over the previous generation. Our world-leading foundational models like Gemini and Imagen are trained and served on TPUs, and Trillium will now power Google's AI innovation at the frontier. Trillium is designed to meet the demands of diverse and rapidly evolving model architectures. The outsized compute to high bandwidth memory is incredibly valuable for training ultra-large-scale dense LLMs and for compute-intensive inference. Trillium delivers up to 4x increase in training performance for Gemma 2, Llama, and mixture of experts models, and a 3 times increase in inference throughput for Stable Diffusion XL compared to TPU v5e. Trillium is the most cost-efficient and sustainable TPU to date, delivering up to 2 times more performance per dollar compared to the previous generation, while also being 67% more energy efficient. And it's not just about the chip. Trillium can scale from a single 256-chip, high bandwidth, low latency ICI domain to tens of thousands of chips in a building scale supercomputer interconnected by a multi-petabit per second data center network. Trillium offers an unprecedented 91 exaflops in a single cluster, 4 times that of the largest cluster we built with our previous generation TPU. Customers love our Trillium TPUs, and we're seeing unprecedented demand for the 6th generation. And now I'm pleased to share a little behind the scenes footage of Trillium TPUs in our data center. One of the reasons behind Trillium's massive performance is that it's backed by the power of our data center network, which has actually been in the making for 25 years, long before we even thought about TPUs. As our user base and the demand for our services has grown exponentially, we've made massive upgrades to our network to handle the unprecedented scale of data and traffic. The culmination of this has been our 5th generation Jupyter data center network. Today, our Jupyter network now supports native 400 gigabit per second link speeds in the network core and an aggregate of 204.8 terabits per second of bidirectional non-blocking bandwidth per block. With 64 such blocks, that's a total bisection bandwidth of 13.1 petabits per second. To put this data rate in perspective, this network could support a video call at 1.5 megabits per second for all 8 billion people on the planet. This is the kind of scale that's needed to support AI workloads. Truly an illustration of just how insatiable the demand for AI computation is. Our data centers support 100,000 plus servers in a single network fabric and maintain 99.999% network availability. And while all our customers are looking for more infrastructure power, they're not all running the same use case. They need the flexibility to choose the infrastructure that is optimized for their workload. This is also why we continue to invest in our partnership with NVIDIA, combining the best of Google Cloud's data center and infrastructure expertise with the full stack NVIDIA AI platform, including the integration of NVIDIA NIM inference microservices with GKE and Cloud Run. At the core of this partnership is the work we do to make state-of-the-art AI infrastructure broadly accessible, highlighted by the recent introduction of A3 and A3 Mega VMs powered by NVIDIA H100 GPUs. Today, we're excited to build on that success with the announcement that A3 Ultra VMs powered by NVIDIA H200 Tensor Core GPUs and accelerated networking will be coming to Google Cloud later this year. A3 Ultra VMs offer a massive leap in performance over previous generations. They run on servers with our new Titanium ML network adapters that build on NVIDIA Connect X7 high-performance network. When integrated into our data center-wide 4-way rail-aligned network, the system delivers non-blocking 3.2 terabits per second of GPU to GPU traffic over RoCE. Compared to A3 Mega, A3 Ultra offers nearly double the memory capacity and 1.4x more memory bandwidth, up to 2 times higher LLM inferencing performance, 2 times the GPU to GPU networking bandwidth over RoCE via NVIDIA ConnectX-7 networking. But it's not just about VMs. For generative AI and HPC applications, you want to use a large number of VMs in a single cluster and maximize performance of the cluster. Today, we're announcing Hypercompute Cluster, so you can run your most demanding AI and HPC workloads on Google Cloud effortlessly. Hypercompute Cluster makes it easy for you to obtain dense, physically co-located accelerators with non-blocking and ultra-low latency networking, and topology-aware placement control. You can deploy and manage tens of thousands of accelerators as a single unit, with features like group maintenance to minimize workload disruptions. Hypercompute Cluster is powered by our Titanium offload technology that is enhanced for AI and Jupyter data center networks. With a single API call, you can easily set up a hypercompute cluster from pre-validated templates for reliable and repeatable deployments. Hypercompute Cluster will be available starting with A3 Ultra VMs. Today, we also get to show you a behind-the-scenes update on our work with the NVIDIA Blackwell platform. We have a few functioning NVIDIA GB200 NVL72 racks and are actively working on bringing this technology to our customers. As a result of all of the investments we've made in AI accelerators, we've been able to deliver an incredible 5 times year-over-year increase in training and inference compute capacity, making it easier for you to access the resources you need for your AI workloads. But not every workload needs that kind of power of a TPU or a GPU. That's why we're continuing to invest in CPUs. At Next this year, we announced Google Axion processors, our first custom ARM-based CPU for the data center. I am pleased to announce today that our first Axion processor, C4A, is now generally available. C4A is a general-purpose VM that delivers up to 65% better price performance and 60% better energy efficiency than comparable current-generation x86-based VMs on Google Cloud. Up to 10% better performance than the latest ARM-based instances available in any cloud. We've seen incredible excitement for C4A from our customers and partners so far, and we can't wait to see what you can build with Axion 2. So we're bringing you powerful new hardware and infrastructures, but we all know that a chip is only as powerful as the software that surrounds it. One of the reasons software is such a vital part of the stack is the critical role it plays in making the development process, from design to build to operate and monitor, much easier. Because to be honest, distributed computing is fundamentally challenging. At Google, we're now using JAX nearly everywhere to make it easier. JAX allows you to express your computations with powerful abstractions so you can focus on the model and the architecture, while the compiler, XLA, does the work of optimizing the implementation for the specific accelerator. To make inference easier, earlier this year we introduced Jetstream, an inference engine for XLA devices. Starting with cloud TPUs. Jetstream is specifically designed for large language models and offers up to 3 times more LLM inference per dollar than previous cloud TPU inference engines. But none of that matters if your costs are through the roof, and that's why we're also making it more cost-effective to run AI and enterprise workloads at Google Cloud. One way we do this is with purpose-built consumption models, like Dynamic Workload Scheduler, which is a resource management and job scheduling platform that improves your access to AI ML resources and helps you optimize your spend. Customers can realize 50% savings with Dynamic Workload Scheduler versus on-demand pricing without long-term commitments. Another source of unnecessary spend is over-provisioning. Retail organizations have typically had to over-provision their network during times of peak sales to manage network traffic. That's why today we're announcing Application Awareness on Cloud Interconnect, which allows you to prioritize your most mission-critical applications during peak traffic periods with the granularity of 6 traffic classes, flexibility in deployments, and a choice of multiple policies. This helps lower TCO, reducing the need for over-provisioning of hybrid connections and dedicated and cross-cloud interconnects. Google Cloud is the first major hyperscaler to offer a managed traffic differentiation solution, and it's available now in preview. Our investments throughout the AI hypercomputer stack are enabling us to deliver unparalleled levels of performance, scale, and ease of use, and cost optimizations for our customers. This is why we're a leader in Forrester's AI infrastructure wave, and more recently, a leader in Gartner's Magic Quadrant for strategic cloud platform services, where for the second consecutive year, we're the only leader to improve on both vision and ability to execute. An incredible illustration of how rapidly we're innovating on behalf of our customers. I'm joined here by 3 Google Fellows, experts who've shaped some of the most critical technologies that power everything we do at Google. Our pace of innovation here at Google Cloud is rapid, but it's important to note that our speed today is the result of investments we've been making for decades. And today you're going to get a rare look behind the curtain at our approach to innovation as we learn from 3 of the Google Fellows who have been the architects of some of the incredible work over the past few decades. And we're truly doing some remarkable things. We operate one of the largest terrestrial and subsea fiber networks, more than 2 million miles of fiber. That is over 10 times more than the next cloud provider, which enables us to deliver quality of service and performance that outpaces everyone else. Our next generation firewall has 20 times the threat efficacy of other cloud service providers. With our internal systems, Borg and Colossus, we built a disaggregated compute and storage architecture, which enables near arbitrary scaling, best performance, and lowest cost. From the beginning, we have viewed our mission to organize the world's information and to make it universally accessible and useful as a problem in artificial intelligence. This lens gave us a head start on understanding the fundamental problems in the space. It is the Google Fellows and technical leads like the ones we will be speaking to today that led breakthroughs like transformers and AI accelerators like TPUs. The result of this is somewhat magical, but it's really just evidence of what the best of human ingenuity, working in collaboration, can achieve. Today, we'll take you a little bit behind the scenes. It's an honor to welcome 3 of the brightest minds in computing to our stage today. Each of them has made profound contributions to the world of technology, not just within Google, but across the broader industry. Jeff Dean has been at the cutting edge of large-scale distributed systems and web search for more than 2 decades, and at the forefront of AI for more than 10 years, leading the development of critical infrastructure like TensorFlow and Pathways. Jeff has truly witnessed and led the evolution of AI from its early days to its current transformative power. Eric Brewer's career has spanned everything from pioneering distributed systems, responsible for some of the earliest work on cluster-based scale-out computing, and ultimately laying the foundation for Kubernetes, truly the foundation of modern container orchestration. Kerry Grimes-Bostock has been a cornerstone of Google's infrastructure for over 20 years, building and scaling systems like Borg and our data centers, which are at the heart of nearly every innovation we have at Google. Today, we're excited to hear from these experts as they share their perspectives on Google Cloud's journey. The dramatic impact of generative AI really can't be overstated. Right? This is a once-in-a-generation inflection point, and it's impacting all of us. It feels a bit sudden, but we know the technology behind it has been the result of decades of technology advancements. So can you each take me back to your early days at Google and share some of those early decisions and how that's shaping us today? Jeff, let's start with you.
Sure. I think you're right. A lot of the things we're doing today in AI rely on a lot of the infrastructure and systems that we've built up and sort of improved over many decades. I think in the earliest days of Google, we were essentially a single product search engine company, and we were working on how do you scale that system up? How do you build systems that can crawl large amounts of the web, index it, serve queries to a larger and ever-growing number of queries per second or queries per day, however you want to measure it. And then at the same time, we were trying to scale up, the size of our index, because searching more pages is generally better for search quality, handling more queries faster, so lower latency, and then also updating the index more often. And those combination of factors is really like one of the really exciting scaling challenges in computing. And I think now we're sort of at a similar point where we're working on how do you build really highly scalable AI systems at scales the world has not really attempted before. Yes. And there's always things that go wrong, and you're right about that. But I think it's an exciting time in computing, and we now have these systems that can sort of see and understand language better than anything we've built before, and that's exciting for what we can do with computers.
Yeah, the parallels with web search are actually really interesting, and you've seen this in terms of sort of the indexing and serving and the transition there, and going through that arc a second time is fascinating. Carrie, what do you think?
Yeah, I completely agree with that. I mean, when we first were doing web search, there were so many things we really had to come to terms with, right? It has to be a good quality product, right? You can index everything in the world, which was a challenge in and of itself, but you have to be able to produce something sensible out of it that people can rely on. They think they're high quality answers. You have to deal with spam and all kinds of junk that shows up and people trying to game the system. And I think the challenges associated with that are really similar to some of the things that we're confronting with AI today. How do we make it, and then how do we use it as a product? And I think the second thing that really came up is just the uncertainty, right? Where when we first tried to do index selection, we did machine learning assisted index selection. That transition was a huge challenge, right? Because there was so much institutional knowledge built up in the existing systems, and we had to be ready to take a risk that we were not just going to use an algorithm to choose the index, but we were going to do it online all the time, trillions of pages a day. And we had to be convinced that over hours, minutes, days, those decisions were the right decisions. Yeah. And that was a huge challenge. And I think we're really dealing with something with AI today. There's the huge scale piece, which we have to get right. But there's also the how do you turn it into a product? How do you make it something someone wants to use? How do you manage all the data that you're moving around and make sure it's the right data in the right place at the right time?
Yeah, the quality signals and extracting those quality signals has been really important. And I think your point on explainability is also key. And our lessons there have been really valuable to us over the years. Eric, how about yourself? What do you think here?
Well, I kind of view this from the same lens I always have, which is really I want to build large-scale systems that are easy to program and can solve really large problems. And in fact, I was working on search even before Google existed because it was the first problem we had in the world. It really required giant infrastructure. Yes. That made it super appealing. And so that work in some sense indirectly led to Borg, but really what happened is in Google, it's very much a focus on containers and processes and APIs, and all our software is built that way. And so it's kind of natural to say, how far can you push that model? And it's a great model for giant scale systems, right? It's really the only model that has been working well. So that really led to Kubernetes, and that's been its 10th anniversary was recently, yes. So that was a lot of fun. And then now we're seeing Kubernetes used incredibly largely for AI. I can't name the customers, but all large players in this industry are building on top of Kubernetes. Yeah. I think it's a fair statement. So it's great to see that transition. And GKE is by far the best way to do that today, and is evolving very quickly in that direction.
The growth of GKE and Kubernetes for AI workloads has been stunning. I mean, it's just been off the charts. So I want to talk a little bit more about some of these early days at Google. You represent a lot of experience here. I know there were some real challenges that we had to solve. What do we have to overcome? I mean, maybe we'll start with you, Carrie. What are some of the hard problems you remember?
Well, talking about Borg and about our computing infrastructure, Borg started off as a way that we'd replace babysitting your machines. The thing before it was actually called the babysitter. And it pretty much let you send your work out into the world and just made sure if a computer died or something happened, it got restarted, it got sent for repairs. And that was pretty much the scope of it, right? Everything else was kind of on you. I mean, that's a very simplified statement, but that's kind of where we were. And Borg replaced that. But maybe about 10 or 11 years ago, we hit an inflection point, right? Because Borg was really managing these high availability workloads like web search, where you go to the server, you need a response fast. And we tried to sort of rethink that and how do we make it better? But it actually, as many systems projects do, some things went better than others. And we had a chance to take stock of where are we going with this, right? And I think it actually turned out to be a great opportunity for us because we had to say, well, what value does this system provide to us, right? How do we make this add more value? And one of the realizations is that we were managing these massive data pipelines, which were not high availability at all. They were, but they weren't, right? They needed to run, they needed to process a lot of data at the same time. But we realized even, accounting for special stuff like indexing, when you looked at our clusters, we were clearly doing work that was different than the kind of canonical computer science work that people talked about scheduling. And so we realized that to be cost effective and to do the work that needed to be done and really respect the things that our internal developers wanted, right? They said, I just want to send my job out and know it'll come back by Friday, right? They don't, they had these different requirements that we need to blend kind of a traditional high availability scheduling with other options. And to do that, we really had to be able to run our fleet at a much higher utilization. We needed to be able to manage jobs much more tightly. And that was, I think, as much as it was kind of a moment when we had to reevaluate what we were doing, it was a really important thing that led to kind of the next 10 years and really supported some of our large data applications, our AI pipelines, our more nuanced scheduling, and also cost effectiveness as a whole as we went forward.
Yeah, very helpful. Eric, how about yourself?
Well, this brings up memories of many little problems we had to solve, but I think the one that probably plays best for this audience is when the early days of Kubernetes, we were trying to get people to use it, explain to them why they should use it. The one that often carried the day was this utilization argument that at the time, a typical VM would be about 10% utilized because it's either not the right size for the job it's doing or no one's looked at it recently. So it was the right size before, but now it's not. And when we got people to move on to Kubernetes and just putting containers on machines instead of jobs on machines, suddenly it was very easy to get to 50% utilization.
Right.
And that ended up being a great sales technique for us, obviously, because that's easy to sell. You don't have to be, but it was not actually what we wanted. So we wanted to sell APIs and processes and containers, but it doesn't matter. What people bought was efficiency, not surprisingly, and flexibility, right? Running different workloads on the same hardware is a hallmark of Borg, and that is another kind of efficiency you get from these systems. So that's still continuing to this day, and AI is just a new kind of very complicated workload, but yet again, just another workload.
Yeah, the evolution from Borg to Kubernetes and now AI workloads synchronously running at scale, that's been incredible to see. Jeff, you always have great war stories about the early days and the experiences we've gained.
Yeah, I mean, I think actually a lot of the systems we've built over the years really are about different ways of managing data, transforming it, getting derived information that you compute from that data. And you can think of that as like some simple MapReduce style computation where you're running on thousands of machines to compute some derived information. But you can also kind of view modern AI workloads, training large models as that. You're trying to sort of take a large pile of raw data and then train a model on it so that it can extract interesting insights from it in the most effective AI model architecture you can come up with that can absorb, whatever information you want to train the model on. So I kind of view that as like, and even Google Search is sort of transforming the raw web pages of the web into something that you can all of a sudden do queries and get useful information out of. So I think that kind of thread runs through a lot of the work we've done over many years, and it's an exciting thread.
Transforming the world's information to an intermediate format that is easily queryable. I mean, that theme seems to underlie 25 plus years of work, I think, represented by multiple aspects of this group. Really, really amazing. Jeff, I'll stay with you. I want to talk about some of the early work that really led to some of the observations that motivated TPUs. Can you give us some background on how you identified the need for TPUs and some early design principles that we came up with?
Sure. So maybe I'll go back even further. I got introduced to neural networks in 1990 when I was a senior at the University of Minnesota. Mm-hmm. And I had a couple lecture class segment on it, on the approach. And I thought it sounded kind of interesting, so I decided to do a senior thesis on parallel training of neural networks, because at that time people were kind of excited about the ability of neural nets to solve really teeny problems in ways that other approaches couldn't, but they didn't really solve real-world scale problems. So I thought, oh, wow, if we just have the 32 processor machine in the department do something instead of one processor, it would be amazing. So I spent a few months on that and came up with a couple different approaches of parallelizing them, neural network training. And you know, you could get them to scale a little bit, but they still couldn't solve really real-world problems. But I felt like the abstraction was the right one.
Right.
So then fast forward to about 2011, and I bumped into Andrew Ng in a micro kitchen at Google. He's a Stanford faculty member, and he was spending a day a week at Google. And I'm like, oh, what are you doing here? He's like, oh, I haven't figured it out yet. But at Stanford, my students are starting to get good results on neural networks using GPU cards. I'm like, oh, that's interesting. So we got to talking, and eventually I decided we should really try to scale up training of neural networks again, back to my undergrad thesis. And so we decided to use thousands of computers because we didn't have accelerators like GPUs or TPUs that didn't exist yet in our data centers, but you could get 2,000 machines, 16,000 cores, all working together to train a single model. And pretty interesting things emerge where like the model could, in an unsupervised way, learn high-level representations of things like cat faces or human faces or the backs of people walking or things like that without ever being told what those were. And so we started to work on speech recognition models as well. And we're getting really good results using neural networks there. But they were computationally pretty expensive compared to what we were using in our production speech systems then. So I started to say, well, if the speech system gets a lot better in quality, people will start to use it more. And if they use it 3 minutes a day, and we have 100 million people doing that, the computational cost of just launching this improved neural network-based speech system instead of the current production one would require us to double the number of computers Google had in our data centers. And so we realized there was a better way. And it turns out we took advantage of two features. One is neural network computations are actually quite specialized. They're essentially lots of different compositions of linear algebra. And they're also very tolerant to low precision. So you can essentially build computers like TPUs, tensor processing units, that are essentially very low precision linear algebra machines.
That's right.
And you get really incredible performance advantages. When we did the TPU v1, you know, the improvements over CPUs and GPUs of the day were about 30 to 80x improvements. And we've sort of had many generations of TPUs after that. But that's sort of the genesis, was that thought experiment of what happens if everyone starts using speech recognition or image models at Google.
It's really unbelievable, Jeff. I mean, you can't escape your youth from your senior year and your senior thesis to bumping into someone in the micro kitchen to building out image recognition, speech, and
you never know when your senior thesis will come in handy again.
Stay in school, I think, is maybe the takeaway here. Eric, Jeff mentioned some of the design principles around TPUs and the lasting impact. What were some of the early design principles you've leveraged, and have they remained consistent throughout your journey?
I think there are some that are deeply part of Google. The most obvious one is, you know, stateless processes are easier to manage than stateful ones, and separating state management out from the rest of infrastructure. I think there's a lot to be said for the kind of the value we get from hiding things behind load balancers. That kind of is how we scale out things. It's also how we deal with a lot of high availability and fault tolerance. Google historically takes its machines down every month, all of them, right? And that requires a lot of not all at once, right? Carefully coordinated, but nonetheless, you know, if you talk to most modern cloud users, they would say, no, you can't take my machine down, right? We have to actually, like, it's got to stay up forever, right? That's my mental model of my machine. And Google Wises, before I got here, was like, that's an unreasonable promise to expect. So let's assume that machines will go down all the time and build our higher level systems to make up for that. And I think that principle still really applies very widely in many parts of Google today. And I think that was, you know, a good choice, and certainly one I still advocate for. But it is not the default choice for people that kind of grew up on running their own babysat machines and clouds, where it's kind of like, oh, I have one of these, it's very special, I've got to make it work forever, right? And so those don't go too well together. One little point I'd add on that, which has been interesting, which is when we try to build VMs on top of processes that get shot down every month, that would normally take the VM out too. So that's also why we had to develop live migration. So that was one of my first big projects at Google, was how to live migrate these things so that we could move them around every 30 days rather than shoot them. And that's still how Google Cloud works.
I remember I learned this from you actually when I was a graduate student, Eric. In one of your early ventures, you showed how you would reboot machines rolling every few days, actually, to keep them safe, reliable, and actually up. And this was 20-something years ago, actually.
Yeah, that was driven mostly because there are large parts of the software stack, including the OS, that we couldn't control, and it would leak kernel memory because people weren't used to making applications that had lots and lots of network connections.
Yes.
The network stack would leak memory. So you were going to run out of memory way less than 30 days from now. And so you had to actually, same thing, the load balancers hiding the fact that we're changing the machines all the time. But yeah, there was a period where we were doing every 3 days, we had to reboot all the machines.
Yeah, that was definitely counterintuitive, but it's been the pattern.
We later fixed the OS, but of course that requires help from the vendor.
Right. Very, very interesting. Kerry, sort of along these exact lines, you've spoken about how Google's rapid evolution of products and infrastructure meant that the traditional CRUD approach, create, read, update, delete, was no longer practical. How did this environment really shape your approach to Borg data centers, and what were some of the design choices you made to accommodate this rapid change?
Yeah, I mean, we've spent a lot of time looking backward, but I actually think this question is reversed, right? I think there's an approach where when we talk about developers, we talk about workflow, right? And what's the workflow and what's the use case? And that's a really important way to look at things. But when we think about the kinds of evolution we've needed to do things like AI, right, to make major product changes, I actually think we have to go back to that older model and talk about what are the data structures, what are the simple APIs, right, like the CRUD APIs that we need, because we don't know what's coming. By the time we fully understand what the workflow looks like, it's too late. Yeah. Right. And there are definitely cases where we need to do that. But I think about the work we do in AI right now, where, one of the things, the primary thing I work on is trying to get these new models to products, right? How do we make them something that's operating in production, has all the stuff that it needs, really works for a product? And we don't know, right? People ask, what are we doing for 2025? And the answer is, we're doing what we need to do. I think we have some great ideas. We think we're doing what we need to do. And I've really been encouraging the teams to assume that everything will change. You have to pick some kinds of basic functionality, some parts of the API that you believe are important. And you have to collect that data, and someone will come up with a new use for it, right? And so really thinking about modular pieces rather than end-to-end workflow. Yes, you want to support that workflow, but how do you do that in a way that gives you kind of components you can play with when the next great idea shows up? Because you don't have 6 months from the time someone has the next great idea to make something that really is going to work. You have 10 days, 3 weeks, maybe 6 weeks, but you have to have pieces you can work with, right? You have to have APIs that you can use to do new use cases. You have to have data structures that you can repurpose, right? I built this thing to tell me if a data set is compliant, but I actually need to use it to enforce during the training loop the things that I want to have happen, right? And so just new use cases come all the time. We have to think carefully about how we build the underlying pieces, things like pathways, bits and pieces that we can use to really shape the next idea into something that's a real product.
Yeah. So the journey here has been astounding. I mean, I think it's safe to say, though, that the journey forward is going to be, over the next few years, probably even more exciting. So looking forward, what do you all think is going to be some of the most promising, but also concerning implications for the future of generative AI and its impact? Kay, why don't we start with you?
Well, I think the thing that I worry about is, how do we use generative AI to access information, to provide information, to support things like captioning or, interacting with people in remote locations, or being able to really summarize data? I think there's some fantastic use cases, right? The things we do with images and medical imaging. But how do we not use it to replace things that really require human judgment as well, right? And I think for me, that's something I really think about is how do we find these really compelling use cases for it? How do we engineer it so we really know that we're delivering high quality data, we have users who trust it, we really understand what's happening to the extent that we can with a new technology. But at the same time, how do we pick the use cases where it really enables new things, helps people do their jobs, helps people interact with the world, find information, get the best results, but not necessarily replace all the things that need to be generated as new information in the world and need humans working with them and exercising judgment, because it's a very different kind of loop that happens in the process.
Yeah, the judicious application of the technology is going to be super important. And Jeff, how about yourself? What do you think about promising and concerning?
Yeah, I think promising, I think there's so much potential in many, many areas of endeavor. I think if you think about education, we're close to having the ability to have something where you could put in some material in a variety of different modalities, be it text, chapters of a textbook or 20 research papers you're trying to understand, or a video of a lecture, and then have a system that can help you in the way you learn best,
right.
Learn from that material. I think the Notebook LM feature that was launched maybe a month or so ago, where you can put in material in one form and you get out a, 2-person AI generated podcast about that. For some people, they don't learn very well from a PDF. They learn better from a conversation. And this could be great for that kind of learning style, and other learning styles should be adapted to and dealt with. So I think education, healthcare,
yes.
The ability to help people get things done that they want at a high level. Can you tell an AI agent, either virtual or eventually physical robotics ones, to go off and do something that you care about? And it sort of does a bunch of actions on your behalf, maybe comes back and asks you some questions about, did you mean this or that, or would you prefer this or that? But enables people to do more. I think that's the aspiration we should have for AI. Is to really figure out how to maximize its potential to help us all accomplish more. And on the worry side, I think there's a bunch of concerns, and one has to be pretty careful about how one deploys AI systems. I think misinformation generation, misinformation could always be generated, but now you can generate it, in a turbocharged way that's very personalized and looks even more realistic in some ways. So that's certainly a concern, particularly this year with so many people going to the election polls in countries around the world.
Yes.
That's certainly one area of concern. I think, deploying systems in ways that are not biased by the world as it is, but instead aspire to the world that we want it to be is what we should do.
Yeah, very insightful. Eric, what do you think?
Well, I've done a lot of work in developing countries, and one thing that's always struck me that I think we can address is the first order developing countries don't have enough specialists. Right? I remember Rwanda had one guy that could read an MRI, and if he was out of the country, then they had 0, right? And so we've done this already some, right? There's been quite a good work around like diabetic retinopathy, getting assistance reading those images, x-rays, things like that. But I kind of feel like if you just broaden the category, like we need specialists in places where there are not specialists. Yeah. And the combination of internet access and AI seems like a pretty complete solution to that for so many specialties. So that's what I'd love to see happen, because it's empowering, right, to those areas. On the worry side, I tend to think about it kind of how I think about databases, where we kind of separate things that are kind of read-only and presenting information from things that where you start to make transactions or changes, right? And those are not too bad either, because at least you can undo those in a database system. So undoable changes are not so bad. And then there's, irreversible changes. And like before we have automated systems making irreversible decisions, I think we need some thought, right? And the risk we're in is not so much, I don't worry about this at Google, for example, is that so many people can try so many control systems over the next decade, and not all of them will understand all of these trade-offs. So we will have some badly design control systems that make bad decisions. And that's going to be a learning decade, I would say.
Yes.
But that's one I definitely worry about.
Yeah, we're going to be living with the positives and the concerning outcomes over the coming decade, and there'll be lots of experience and policy that we're going to have to develop. Keeping the focus on the future, and Eric, staying with you to begin with, what are you working on next? What are you most excited about right now?
Lots of things, but I would say the ones I'm working on most are kind of what's next for Kubernetes, and AI is a big part of that story. It is a good foundation for AI, but it does nothing particularly special to enable AI or make AI workloads particularly easier to do, especially given how much different stuff is going on under that single label, right? It's quite complicated. That actually is a place where a little more structure could help applications be easier to write and easier to use. So we'll see if that can go somewhere. Still doing a lot of work on open source and open source security. We depend on open source at Google, but we also depend on it for all of our critical systems, whether that's water utilities, pipelines, electrical grids, and those are now subject to nation state attacks. It would be nice if we could fix that, right? Not trivial, but I think an important problem that I'm also working on, and a few things related to that. But that's probably a good place to stop. Those are two big enough
Two big ones, absolutely. Well, very good. How about yourself, Gary? What are you excited about?
Well, I have some stuff that is a continuation of, Borg and compute work and just the scaling that Jeff's been talking about, and how do we really get there, right? And people thinking about having these big monolithic sort of supercomputer models versus being able to be much more flexible and take advantage of all the great chips and all the stuff that's out there, but also just opportunistically, how do we train models, right? How do we just go out there and say, okay, I've got room today, how can I make this better? And have that really seamlessly fit in. And I think the other thing that I've been very interested in on the data side is, we're moving to more multimodal, right? You put in text, you get speech. You put in speech, you get video. You put in video, you get who knows what. It may be whatever's most appropriate, right? And I think figuring out how to manage all of that data and make sure we're producing results that really are good quality in all the ways we think about quality, right? That are helpful to people, that help them with whatever they're doing, but also, that respect kind of the opportunity of not producing fake images, and what data we have on hand and how we use it and how we get it to the right places is a big part of that process as well.
A lot ahead here. Jeff, how about yourself? What are you seeing as next?
Yeah, I guess a few things. So one is I'm one of 3 technical leads for the Gemini model building effort.
Small responsibility.
Which is like an exciting project with lots of amazing people working on improving our models, giving them new capabilities. One I'm particularly excited about is the long context capability we introduced in Gemini 1.5, where instead of a few tens of thousands of tokens, the models could get inputs that were as long as 1 million or 2 million tokens, which is like 1,000 pages of text or a 2-hour video or 20 hours of audio or something. And I think the interesting thing about material in the input to the model is it's got a very clear view of that. So it tends to hallucinate less, and it's able to sort of refer back to like these paragraphs, or extract like all the results from the 20 papers you put in, and like transform them and put them in a useful form for you based on what you ask the model to do. So I'm excited about how do we push that to the next level, which would be not just here's 20 papers you give the model, but how can you actually get, potentially all information in the context window in some useful form that the model can pay attention to.
Yeah.
And then the other thing I'm spending a bit of time on is like interesting new approaches to hardware. Starting to think about that.
Continuing in the tradition, a lot of opportunity there ahead. Okay, let's, I think, maybe compose the two, the past and the future. So what have been some of the most surprising aspects of the way that Google has grown over the past 2 decades? Maybe we'll go back to you, Eric.
Well, obviously, entering the cloud space was a big transition. And I think it's one that Google was probably not as ready for as it thought it was. I think the reason it comes back to this fact that Google has especially then, a very unique architecture that's great for large-scale systems, but it's not great for babysitting lots of pets, which is kind of what VMs and clouds were at the time. And so, that's a two-way street. We have to learn how to support the workloads that people wanted to run, and that took a while. And other enterprises are not like Google, right? Just because we know what Google wants does not mean we understand what cloud customers want.
Right.
So it took us a while to learn that. But that being said, I think there's now built a large capacity to understand and serve enterprise customers that didn't exist before. And that whole transformation has been a great fun to be part of. Let's try that again. So that was certainly entertaining at times, but also I think transformative for Google.
Yeah, that I think has been an incredible journey, and the success that we have, and also the AI opportunity really comes back to our strengths, and that's been also interesting to see as this sort of AI revolution in infrastructure has taken hold, going back to some of our core capabilities, whether it's TPUs, Borg, Kubernetes, and how that really plays to the heart of AI and cloud has been exciting. Jeff, let's go to you. You see the future clearly, but what's been surprising?
I think one thing that I really like and appreciate is how timeless the company's mission statement has been. I think we've been working on this journey for how do we take information and make it universally accessible and useful.
Yes.
And, the early days of search is, a iteration of that. The most recent AI models that can, learn from lots of information in the world and transform it across modalities, and also how much is left to do that still fits in that mission.
Yes.
Why can't we should make all information available in all languages in the world.
That's right.
Or be able to transform any information into the right modality for the person who wants that information, regardless of what its source modality is. Right. And I think these are really hard computer science and AI problems,
yes.
And there's plenty to do. But when we accomplish some of these things, users will benefit, and that's going to be amazing.
Yep. No, the timelessness has been absolutely surprising and invigorating, I think. Carrie, what do you think? What's been surprising for you?
I think it's been surprising how applicable some of the things, as Jeff said, that we did earlier, it turned out to be to other products, even in cases where we didn't even understand at the time that was going to be true, right? And I think we see now some of the pieces that were built for traditional web indexing, right? That labeled documents, that labeled images for web indexing, suddenly we're putting all this load on them, right? We're using them for all these new things in the AI space to make sure we have the right results, to be really fast with some of this. And in some cases, we're feeding some of the new generative AI back into those pieces to improve the existing products, yes. Right? And I think it's been both, having been around for a long time, not as long as Jeff, but, quite a while. I think, initially a lot of these things were sort of built on the spot, right? We knew that we didn't understand how to respond in certain languages, or we didn't understand what aspects of the web made a page really good in India versus what it would look like in North America or something like that. And we had to tackle some of these problems just from, experimental results. But now as we move into other areas, whether it's something with photos, it's something with a customer in Google Cloud who has a specific need, or it's some of the generative AI work, we're seeing that we can actually, feed through some of that expertise, but also we can feed back in the new things that we're bringing in, the new models, and they actually improve some of that underlying very basic stuff at the core, right? And I think that's been a pretty exciting opportunity to bring it all together. And I hope that that's sort of the direction we go with some of this work too.
Yeah, the timelessness has been fantastic. Look, I've loved this conversation. It's been a privilege to have you all here. Thank you, Jeff, Carrie, and Eric, for joining us today. It's been really amazing to hear firsthand how your work and that of countless others, of course, at Google, laid the foundation for today's pivotal AI moment.